Hello, my name is Mario Spradley, master's student at University of South Florida. This is going to be my master's program project course. The title of my project is going to be Solar Plant Optimum Size, Considering Losses as it Pertains to Avoided Cost. What I'll do for this project is research what other engineers have deemed to be a threshold for a profitable cost margin based on current market avoided costs of approximately 0.037 cents per kilowatt hour. This will have to take into account losses associated with DC to AC conversion, panels, transformers, distribution, station services such as tracking and transmission of the power. I will then model this entire configuration losses in all in an industry standard power program such as Power World. This will show the electrical losses along the path to the end user and give a comprehensive look at where the largest losses could be and where to focus efficiency improvements efforts in the future. The objective of my project is to create a software tool to determine avoided costs. For example, a clean Excel spreadsheet with user inputs. Develop a simulation showing losses as power is received via the solar panels out to distribution load. Research expected outcome from the previous studies to determine necessary megawatt size of solar plant to reach avoided costs. Use simulation to demonstrate a functional unit at 2 megawatts and the output taking into account modeled losses, and also show a simulated grid showing the research determined megawatt output taking into account the modeled losses. Make simulation able to accept user input for scalability for future use in the industry. The benefits of my project will be that solar energy is not only a sustainable source, it is also renewable, and this means that we will never run out of it. The creation of solar energy requires little maintenance. Solar electricity power plants produce zero emissions and make no adverse mark on the environment. Understanding of losses associated with a solar plant. With the EPA regulations starting to change and affect our older, more environmentally less friendly power plants, it's obvious that the future will have to be a more clean power plant, and one of those power plants will be solar. Avoided cost is essentially the marginal cost for a public utility to produce one more megawatt unit of power. A utility will commit the required amount of its power system to meet the daily expected peak electrical loads, plus a reserve margin to maintain service in the event of a power plant failure. If a QF delivers energy into the utility system, the utility will reduce the amount of energy generated at their most expensive operating plant, which, as I spoke earlier, is probably going to be your coal plant. The energy-related costs of that avoided plant, which are typically the cost of the fuel, and a portion of operation and the maintenance costs, comprise the energy component of avoided costs paid to QFs. Avoided costs can be short-run avoided costs under 10 years and long-run avoided costs over 10 years. Of course, with solar, the long-run avoided costs will significantly reduce the avoided cost of the overall unit. So I'll stay within the 10-year short run avoided cost to have a reasonable value associated with our cost. An example of some of this avoided cost is the inverter cost versus the transformer cost. As you can see from this graph, inverters are quite costly. Transformers pretty much stay within the same value of each other, but the bigger the inverter you'll need, the more expensive it will become. This is also the case with the losses, because the bigger the inverter is, the less efficient it will be, and the more losses you'll experience at that device. So as we take into account the avoided costs, we have to take into account the inverter cost, transformer cost, panel cost, and things of this nature. This is a model I'll be utilizing for the inverter and its losses. This is a 3-phase voltage source inverter losses model where the ideal transformer simulates the 3 legs. The turns ratio, as you can see, is set at 2 at the primary side due to the AC out voltage range of a single phase leg is approximately plus or minus 1/2 of the DC voltage. The control sources, current source of IS 1, 2, and 3, and the controlled voltage sources DC 1, 2, and 3 are used to model the switching losses and the conduction losses of the 3 legs. This can be done in PSpice. I will utilize this in PSpice to verify my mathematical analytics are accurate. Here you can see a one-line diagram, which I use PowerWorld to produce this one-line diagram. You can see from this one line, you'll be able to see the megawatt flow and losses that as associated with each individual device. Generator in this case would be your solar panels. The inverter will go from DC to AC, which will be from research showing that most of your loss will be due to the inefficiency of the inverter. That inverter will then go through a transformer, which will move the megawatts to a transmission level kilovolt. That kilovolt will then be passed down to the load level, which would be your distribution substation or distribution switchyard. My project schedule, as you can see in front of you, will be portions of it have already been completed as it is currently February 8th of 2016. So as slated to do my project design review via YouTube. From there we'll receive feedback from the advisor on that design review. I will step into the literature review and the Gantt chart for my final completion of the project, which will be the website completed and papers written, which is going to be done April 26, 2016, which will also be the conclusion of the course. Personal information. I received my bachelor's degree in electrical engineering from the University of South Florida in 2010. In 2010, I moved into my field of expertise. At that time, I became a co-op student at Seminole Electric Cooperative Incorporated in Tampa, Florida. After just 5 months, I was brought on as a permanent employee in System Operations Department. I was certified as a reliability coordinator by February of 2012. I remained in this capacity for 2 years, learning the ins and outs of switchyards, transmissions, power plants, and our SCADA system, which is an OSI system. In February of 2014, I was promoted to EMS SCADA engineer. In this position, I was responsible for assuring the accuracy of the databases and the tools and the usefulness of these tools for system operations. Within 1 year, I was promoted to lead EMS SCADA engineer, where I was responsible for SCADA design and for assisting with the technical development of electrical utility standards for smart grid and automation design techniques and systems. SCADA and smart grid design, technical writing, and development of standards and specifications. I do site visits to client sites, conceptual and detailed design documentation of creating, modifying, and or reviewing substation design assets. SCADA points list, RTYD settings, currently implemented, standards and or device configurations. I am currently in the capacity of lead EMS SCADA engineer with these responsibilities. More information can be found on my project at msee-p-solarplant.weebly.com. Thank you for your time.